Hello, everyone. My name is Bora Ulaşbakandı, and I'm the leader of Group 4. We're going to be doing our presentation on our data pre-processing and initial model results of our data set today. My team members are Doğan Berkay Sözer, Mahmut Furkan Bakal, and Zeynep Nedet Ulaş. So to refresh your memory, I'm just going to do a quick summary of our data set. It's a collection of ultrasonic sensor readings to help train robot navigation algorithms. It's made specifically for wall-following robots and interior spaces. And as you can see in the figure, we're expecting this model to work this way and get used with robots in interior spaces, navigating around the room's perimeter, steering clear of walls and obstacles. And our aim with the project and our implementation is to create a model that can reliably help wall-following robots navigate without collisions or other issues like getting stuck against difficult geometry. And as you can see in the figure, we have a wall that has both concave and convex corners. A robot must be able to utilize all of its sensors to navigate a room that it might come across during its operation. So once again, why are we employing machine learning as opposed to traditional algorithms? Well, residential robots in the commercial space, especially for cleaning, have been available for a long time, so it's by no means a new concept. However, the navigation algorithms that they're typically limited to are those that scan the room beforehand. This is when a robot stands stationary, scans the room, and uses the sensors to gather a depth map to extrapolate the room's geometry. On the other hand, it can also be pre-programmed, but this is rare in the commercial space. Both methods are somewhat inefficient compared to what we plan to do. And our first goal, obviously, is to eliminate the need for preliminary environmental scanning and eliminate the need for pre-programmed algorithms. With machine learning, we can develop a more versatile algorithm for commercial applications. So robots might navigate all sorts of different layouts, different interior layouts, and that's not including factors like furniture. So we make a versatile algorithm that makes it easier for the customer to use this product out of the box and without the need for pre-programming or having to scan an environment. And we believe this is a positive value proposition since the robot can navigate the environment in real time using smart algorithms. So our goal for pre-processing this data is to obviously transform our data into a format that can be easily interpreted by machine learning algorithms, since a lot of algorithms require certain formats and data types to function properly. We need to find the appropriate model and to train and test our data set, which we will go into detail shortly. Now, Zeynep will continue with our pre-processing implementation.
Our initial data set had almost 5.5K samples, 24 numeric features, 1 categorical outcome with 4 classes, and it was imbalanced. We needed more samples, so we we added a class and we used SMOTE to deal with the imbalanced data set. So the one of 2 preprocessing methods we used was using SMOTE. So next slide, please. You can see the description of it here. It used k nearest neighbors to randomly select from the neighbors and generate a synthetic minority instance. Next slide, please. Then we had almost 8K samples, but we wanted more, so we added a new class. We have 4 classes called sharp right, slight left, and move forward. We added a sharp left turn class, which was the inversion of the sharp right turn class. Next slide, please. So as you can see here, before you doing SMOTE and adding a new class, our CA values were lower than after we did SMOTE and added a new class. We have more data and our CA is higher now, and we used KNN to show that. Now Berkay is going to continue with some other preprocessing we did.
Thank you, Zeynep. And I hope my sound is coming. And in the light of the feedback we received from you last week, we used the orange instead of Python for one-hot encoding. With this technique, we increased our targets class number from 1 to 5 and gave them the names move forward, slide right, sharp right, slide left, and sharp left. The purpose of doing this was to increase the readability of our dataset and it's become the more understandable. Next slide, please. But when we use one-hot encoding technique, we noticed that the widgets such as the test and score or the tree or the KNN give the target data error because of our increasing target numbers. As you can see, as you know that Zeynep talked about, for the one-hot encoding, we had just one class, one target variable that is the 1, 2, 3, 4 for the turning styles. After adding the new class, we had 1, 2, 3, 4, and 5. And after one-hot encoding, we had 5 different classes and 5 different columns with that one. And if the, for example, robot moves forward, we make the move forward 1 and the other 0, but this gives us error, and as a reason for this error, we decided not to make our target class more than 1 classes. We can move on. And for our feature,
let me Doğan,
yeah.
explain something for you. Mostly we use the one-hot encoding for encoding the features, not the target.
Okay.
Okay, for the
Okay.
features. Then, if you apply this one-hot encoding, instead of using categorical values in a column, in a feature, then you create, as you show, 4 or 5 other columns as a new features, which explains data better to a model. That's the reason why we would use a one-hot encoding in features. But in target value, you can do like that if you're really interested in, for example, when to right turn or left turn. If you go to the previous slide, then you can here actually, if you go back, here you can actually create 5 different models. One model for move forward, one model for slide right turn. Do you understand?
Yeah, yes, I understand.
After that, you can ensemble these models to decide the final movement.
Okay.
You remember last week or this week actually, 2 days ago, I explained about the assembling approach in machine learning. Remember, random forest is an assembling method for decision tree. I also explained in the class that orange tree has a widget for assembling model. So actually you can do this with this widget. You can train, for example, 5 different models. One decides move forward or not, 1 or 0. Then you can put all the results together to give me where to go.
Okay. Then we will make that according to your preferences and the feedbacks in the next week.
If you like. I am saying that if you like. But if you don't like, just apply the one-hot encoding in features, not in target.
Okay, thank you. And now, after applying the one-hot encoding, we decided to not use that one. And for our feature engineering and the feedbacks we received from you last week, we decided to make the sensor merging. For this, we decided to merge sensors in 2 different ways. First one is the forward sensor creation. And for the forward sensor creation, we combined V2, V1, and V24 sensors, which is the forwards sensor. And for the front right side, we combined V23, 22, 21, and 20 for the front right side of the robot. And V19 still the same because it is the 90 degree on the right side of the robot. And for right rear back, we have 4 sensors, V18, 17, 16, and 15 for the right back side. And the back, like the front, we use 3 different sensors, which are the 14, 12, and 13. And the left rear back, we use 4 sensors again, V11, V10, V9, V8 to control the left rear. and the V7 stays the remain because of its controlling the left-hand side. And left front side, we use V6, V5, V4, and V3 for the front left side control. And we can move on to the next slides. After combining these sensors, our number of data was not lost. So we had the 11K, and after that we have 11K, and our 25 numeric feature decreased to 8. That means our dataset becomes more easy to read and understandable. And we can move on. And in the table, you see on the left, the top train, the top table, the upper bound table shows us our train result after combining the sensors, and the below are the test result after combining our sensors again. I'm sorry, I will make the sentence again. The top data showing us the result test, and the bottom is showing us the test. Train test, yes, I'm sorry. The CA result is 95% on the KNN model with the test, train, and our CA point up goes to 91%. And
Berkay, I think
yes,
that they belong to the results of testing, both of them. But one of them belongs to testing with the data, new features, the other with the original feature, right? But they are the result of the test data.
actually, no, yeah.
Actually, the one of them is for the training results are, and the other of the test result. And I will explain of the comparison of the original data sets
Yes.
of these results.
Okay, then
Yeah.
let me explain something. If you go back in the previous slide, one more, please. In the orange, if you right-click some widget, you can rename it. For this
Okay.
kind of reports, please click rename accordingly the widget. Okay. So in
Okay.
the reports or the screenshots, you could understand what you are talking.
Okay.
All right.
Sorry for that.
All right.
Yes.
Thank you. Let's continue.
And after that, in the right-hand side table, we have the feature constructor, that the features that we have created for the front, left, right, front and back, left, front and back, forwards and backwards. I simply get the average of them with the multiple adding them to each other and divided by the how many sensors that I used. And now Furkan continue with the second sensor combination. Thank you.
Thank you. Hello everyone, I am Furkan.
I
And
just
also
have a question. I didn't understand that now. The number of the features increased or decreased? I didn't understand this.
Number of the features decreased. We had the
Why
20
decreased?
Because we had 25 numeric features,
Yes.
but after combining this, we had 8. But the feature sample row, we had the same rows.
Okay, I
We had
understand. But as a general approach in machine learning, we would like to increase the features. Of course, the samples, but if the samples are the same now in feature number of features. If you go to next slide, if I were you, I would add these features as new features. Do you understand?
Yes.
Because you are not sure that if these features are perfect or not. You are not sure. But if you provide these new features plus the existing features to a machine learning model, it can decide which features maybe it can use.
Okay.
So therefore, maybe in your final report, you can add the third option. First option is the given features. Second options here, using only the augmented features here. The third option, original plus these.
Okay.
Okay, do you understand, Berkay?
Yes,
Okay,
I understand.
Please continue.
Okay.
Okay, hello everyone, I'm Furkan, and I also performed a different variation of the combining process that Berkay just mentioned. And this time, if we consider our report as a full circle, I kept the sensors at 0, 90, 180, and 270 degrees constant. And I arranged the other sensors to have three sensors in each quarter. And as you can see in the graph, and I create new feature by combining sensors. For example, in the first quarter, 20 sensor 20 and 21, and sensor 23 and 24. And after applying the same process in 4 quarter, our feature count, which was the 26 at the beginning, decreased to 17. Because we think that when we create our new feature, we need to remove the older ones. So
But Furkan, you understand what I mean, right? So you can actually put the features together to increase your chances.
We create the new ones and we remove the old ones. That's our mistake. And we use the feature constructor widget in the orange tree to implement this process. And you can see the formulas. Please, next slide, please. And you can see the formulas used to create these new features in the right side of the page. And also in this slide, you can see the test and train results of the KNN models used on this dataset. And on the next slide, we will see the comparison of the variation. Next slide, please. And here you can see the comparison values of the test and train data of the model with smooth and create class operation applied, and the test and train data of the two different feature combination variation. And unfortunately, our categorical accuracy is decreased on the two version of the combining feature because of we remove the.
Now you understand, right?
Yes. And we think why our train and test accuracy is decreasing. We think that we couldn't find.
But now you have the light.
Yes.
Thank you.
And finally, please next slide, please. And finally, based on the test results we experienced, we decided to use our dataset with smooth and create class operation applied, but without combining features, because we think that our categorical accuracy will decrease. And here you can see the final version of our datasets. And finally, we have nearly 11 key data. That's highly balanced, and it's ready for supervised learning and multi-class classification. That's all. Thanks for listening, class.
Did I miss Zeynep?
No, she
No,
presents in the
hocam.
seconds.
Yeah.
She talk about the smooth and creating new class.
If you go to slides back.
Second.
2 slides back.
Oh, it's not responding. There
Yes.
we go.
Here, I think you need to put the 4th result, because the first result should be the original data set. The second must be the data set with smooth.
Right?
Actually, I'm sorry for interrupting. May I add something?
No, of course.
The Zeynep talk about our 5.5K sample and the smooth and the 5th class adding style. And after Zeynep talked about that, we think that we don't need to use that because our CA accuracy is getting higher. So we think that we don't need to put it in here, but we will use that in the next slide that we will present.
Yes. And instead of providing these screenshots, is okay, but it's not easy to follow these, right? When we watch this presentation, it could be a good idea to put it in a figure, right? In a bar chart, in a diagram somewhere, right? Do you understand?
Yes, you are right.
Presentation of thank you for the screenshots, but it's not easy for us compare the results, right? You can use the color coding, right? Legend, and you can give them correct names, not train 1, train 2, but base. So I would like to see in your final report 4 results with respect to train and test in 2 different diagrams. But in train and test, we can see the, each before pre-processing with smooth plus işte version 1, smooth plus version 2, for example.
Okay.
Right?
And I
But
want to ask a question.
maybe the fifth option will be what? Fifth option.
Yes, I asked this. Should we use the without removing our old features?
These are, of course, you do it this.
Yes.
But you can add the other one, another option.
Smooth with the versions.
No. Plus V1 plus V2 plus the original feature.
Okay.
Okay.
Do you follow me?
Yes.
Yes.
So give some appropriate names and then compare. And now go to the last slide. I believe that you report your final data set, right?
Yes.
But I think you will change this.
Yes.
If you put all together the new features, I believe, in the end, I believe that smooth plus version 1, version 2, all together with the features.
Yes.
Okay.
Yes.
I think so.
Yes.
But please just change these three and present a compact representation of the results and then update this. Okay, I like the presentation. That's what actually,
Sir,
at least I am expecting this kind of presentation. Okay, at least this is good. At least you understand what I expect from you. Thank you.
Sir, if I have one comment. First of all, thank you for the feedback. I should say when we combined our features, we originally went in with the intention of decreasing our number of features for optimization, purposes. But so we never, unfortunately, we didn't consider combining those new features with our original sets of features. But that's something we'll definitely do.
Yes, thank you. And more for your features, can you do any normalization? Do you need any normalization?
Zeynep, you can explain it.
We thought about doing min-max normalization, but our data or samples are already in the range of 0 and 5, so it's readable. So we didn't think it was necessary.
But you might try, right? You might try.
Yeah,
You can
we
report
tried.
that maybe it does not make any improvement, and we keep it like that, for example. But in some models, it is important, In linear models, for example, it is important. You were saying something, Zeynep?
No, Jam. We tried it, but it didn't look like it did anything.
Okay, but in your presentation, show us your experiment saying that we tried this, but it didn't work.
Okay.
Okay.
Since our dataset is not linear dataset, we use, but it didn't mean anything to us, so we didn't put it in here, but we will. Okay, thank you.
Okay. So, and by the way, to sum up these readings is logical to decide the movement. We have,
Actually,
thanks to mechatronics engineering department, we have a student from there, Bora. Can you explain, is it a good idea to sum up the readings from the same direction or similar direction sensors? Or should we use something different?
Well, in our case, for interior spaces, which is what the robot is mostly intended for, we're looking at mostly straight walls or furniture with mostly straight edges. So what we tend to see is with different angles of sensors, there are no extreme protrusions or extreme values from one sensor to the next. So if one sensor has a certain reading, another sensor tends to have very similar reading, and if it has a different reading, then it's an indication that there's an extreme situation in terms of the topography of the room.
Okay, I mean that, for example, if you go back to that slide, your explanation plus, you get the average of it, right? Here, for example. Yes.
Yes.
If I were you, I tried maybe the summation on.
So the summation without dividing by the number of sensors?
Yes. Because,
But
for example, in right front, if you do the summation, then you will get much more information to turn you said right, for example, right front will get much more result, right?
Yes,
I don't know.
since we divide by the number of sensors, each individual sensor has a smaller effect. If that's what you're saying,
Yes.
then there's
Instead
some
of summation, you are just also making difference between these regions.
Yes,
Because
we
in
lose.
here,
Yes, we
the
lose some
regions have
accuracy.
some average numbers, right? Average reading numbers.
Yes.
yes,
But if what I am suggesting that just do not average it, just sum up it up. If you sum them up, maybe you could get very different results. What do you
Okay.
think?
Yes. We think it's a good idea. We will definitely try
Then
that.
you can try, right?
Yes,
Yes.
yeah, we will try.
yes, we will try.
Okay. So keep in mind that most of the time you would like to increase the number of features, not decrease. Okay.
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 All right. And thank you for the presentation. I like it. It's very understandable. It's very good, easy one. Thank you. You can improve this, but this is at least what I am expecting from you. I understand that you read the documentation and follow it. Thank you.
Thank you.